This video describes a procedure first added to Statgraphics version 19.7 for spectral clustering. Spectral clustering is used to assign multivariate observations to groups with similar characteristics. Unlike clustering methods such as k-means, spectral clustering finds clusters based on connectivity between points rather than closeness. It works better than procedures like k-means when the clusters have unusual shapes. As an example, consider this plot of 200 observations in the space of x1 and x2. It consists of 100 observations in each of two crescents. We would hope that a clustering algorithm applied to this particular data would properly identify those two crescents. If we ask the k-means clustering algorithm to divide these 200 observations into two clusters, this is the result. What k-means tries to do is divide the data into groups around two centroids, ending up with basically two convex shapes. It misses, unfortunately, the true pattern of this particular data. There are four basic steps in spectral clustering. In the first step, we construct an affinity or similarity matrix between all pairs of observations. A popular method for doing so is based on identifying each point's nearest neighbors. We then construct a Laplacian matrix from the similarity matrix. A Laplacian matrix shows how connected pairs of nodes in a graph are to each other. The third step is to project the data points into a lower dimensional space based on the eigenvalues of the Laplacian matrix. Finally, a standard clustering algorithm such as k-means is applied to the data in the lower dimensional space. A good way to think about how spectral clustering works is to imagine bridges between all pairs of points. In order to travel from any point in one crescent to another point in that same crescent, you could travel across only short bridges. On the other hand, to travel from a point in one crescent to a point in the other crescent, you'd have to go across a long bridge. In forming the clusters, spectral clustering cuts the longest bridges first. If you select Spectral Clustering from the Statgraphics Multivariate menu, the first dialog box will ask for the names of the columns containing the data. You can also specify point labels if you have them. The next dialog box that appears is the Analysis Options dialog box. The first thing you need to specify in the upper left corner is how many clusters you want the algorithm to create. You can then choose between three methods for estimating the affinity or similarity matrix. In this case, nearest neighbors performs best. There are three methods for making the final assignment of clusters. K-means is very popular. There's an option for randomization. If you fix the random seed, then if you repeat the entire estimation process again with the same data, you'll get the same result, no matter whether or not there are random assignments being made. You have the option to standardize the variables, that is, subtract the means and divide by the standard deviations. That's important if your variables are in different units. Verbose output applies to the output from Python. Estimation gives various options for the different steps of the algorithm. If I'm using nearest neighbors, one important input here is the number of neighbors to consider when creating that affinity matrix. And finally, near the bottom, I can specify how I would like cases with missing values to be treated. As part of the output of all clustering algorithms in Statgraphics, you get an analysis summary. This summary displays a variance analysis, a cluster summary, and tables of the cluster centroids. In clustering such as k-means, where the regions created are approximately convex, statistics like the final inertia, variance explained, and the Kolinsky-Harabash index can be used to help determine how many clusters there are in the data. Unfortunately, the variance analysis is not particularly relevant when doing spectral clustering. The best way to judge how well the algorithm has worked is to look at the 2D and 3D scatter plots. Here you see that spectral clustering has perfectly identified the two crescents in this particular data. For fun, I also asked the spectral clustering algorithm to divide the data into 8 clusters. It gave me this very reasonable result. There are two major advantages of spectral clustering. The first is that it works well when there are complex, non-convex clusters, such as in the data we've been looking at. Secondly, unlike some clustering methods, spectral clustering is not sensitive to how the procedure is initialized. If you'd like more information about spectral clustering, here are two references. The first link is to the documentation for the spectral clustering procedure in the Python scikit-learn library. This is the procedure that's being called by Statgraphics. The second is an overview article by Dilip Kumar called Spectral Clustering Algorithm. Both of these references are worth looking at.